start. Great pleasure today to have Professor Andrew Steiner from the University of Tennessee at Oak Ridge National Lab. So Professor Steiner is an expert in neutron stars, so the nuclear physics of the interiors, as well as the physical observations. And I have seen Andrew give a number of talks over the years. The last one was on the fateful morning of August 17th by complete chance. I have to admit, I wasn't able to give it my 45 to 10 minutes better this time.
Thank you very much. Thank you very much for having me. It's a pleasure to be here. So I'll talk on the nature of dense matter from multi-messenger observations of neutron stars. Now we can do the multi-messenger thing. I have to acknowledge for the particular work that I'm talking about today, I mentioned my list of collaborators. In particular, I want to highlight at UT my graduate students, Spencer Boulogne and Xingfu Du, and my postdoc, Sophia Han. And then I have several collaborators, both from astronomical observations and nuclear theory and sort of astrophysics theory. But I'll just go ahead. What? Does it really not want me to? Oh, that's interesting. OK, fine. I accept. So I'll just introduce to talk about neutron stars and the equation of state of dense matter, and highlight some recent work on quiescent lumens X-ray binaries, and then put this in the context of LIGO. And then I want to go beyond this simple neutron star structure and talk about neutron star cooling, the thermal properties, and a little bit about the methodology, superfluidity in dense matter, and how those are connected. And then finally, at the end, we need to do numerical in order to understand the observations completely, we need to do numerical simulations of core collapse supernovae and neutron star mergers. And so we need to figure out how to input the correct nuclear physics to make those simulations accurate. So my PhD is actually in nuclear physics. I come from the QCD world. So I like to motivate this from looking at something like the Qcd Phase Diagram. Here, this is baryon chemical potential. You can think of this as a proxy for density and temperature. And so if you want to probe this high density, low temperature region of the Qcd Phase Diagram, then neutron stars are exactly the one place in the universe where you can do this. Okay? So you can think by analogy to the phase diagram of water. Now, the axes are different, but water, of course, is very complicated. As you reach high pressures and low temperatures, there's all sorts of different forms of ice. And it's not unreasonable to expect QCD might also be complicated, that the ground state of matter at low temperature and at high density could have some exotic properties to it. Heavy ion collisions and lattice QCD are different techniques in nuclear physics, but they're not really sensitive to these high density, low temperature regions. So, of course, we want to talk about neutron stars. This is a plot that I've adapted from a famous plot by my colleague Danny Page, just sort of summarizing some basic features of neutron stars, but just for the purpose of this talk, I'm going to just go from the outside in, the outer crust of the neutron stars, essentially neutron-rich nuclei, similar to what we are familiar with here in the laboratory. And then as you go higher in densities, these nuclei become more and more neutron-rich until eventually you reach a point at which it's energetically favorable for some of the neutrons inside the nuclei to leave, and they form a background, these unbound neutrons form a superfluid. So you have neutron-rich nuclei embedded in a sea of superfluid neutrons. And then at a higher density, about 10 to the 14 grams per centimeter cubed, we convert to the core, where you just have a fluid of neutrons, protons, electrons, and then nobody knows what the real composition of the inner core of the neutron star. And I think of this as the sort of holy grail question. What is the neutron star composition? Okay? Or in a language that might be more comfortable for some of my nuclear physics colleagues, you think of describing neutron star matter in terms of an effective field theory. And so in order to write down the effective field theory, one of the first things you would like to know are what the correct degrees of freedom to describe that correct effective field theory. It may be neutrons and protons, it may be hyperons, it may be deconfined quarks, or alternatively, the degrees of freedom in the very center of the neutron star may be completely different than the degrees of freedom we're familiar with from understanding vacuum physics. Hyperon is just a neutron or proton, a baryon with some strangeness. So the prototypical hyperon is lambda hyperon, which is just UDS. And so that's the lightest mass hyperon. I also mentioned Bose condensates. There are some theoretical models which suggest like pi minus or k minus condensation. So pi minus being U bar D and k minus being U bar S. So one of the games, well, let me start. Neutron stars, in part because of the extreme densities reached, they're compositionally uniform. Unlike planets, there's no gas giants or rocky planets. All that's very simplified to some good approximation. If we ignore rotation, which I will for most of this talk, all neutron stars in the universe lie on one universal mass radius curve. And so if we do enough observations, we can just connect the dots, and then we know the curve, and we know something about all the neutron stars in the universe. Because of Einstein's field equations, there's a one-to-one correspondence between the mass radius curve and the equation of state of matter. Okay, this is just you put particles in the box, and you compute the pressure in this box as a function of the energy density. And so this is the equation of state. This is fundamentally a nuclear physics QCD type quantity, but there's a one-to-one connection to the astrophysical quantity. And so this has been there's a paper by Al Cameron in 1959 that says, we want to do observations of neutron stars to learn about dense matter. Okay, so this has been a long story. A couple of the critical things are a couple 2 solar mass neutron stars, and you can think of these as just observations which are horizontal lines. And so the curve must go high enough to cross those horizontal lines, the theory curve, if you like. About 10 years ago, I think neutron star radii were, from the theory side, thought to be between about 8 and 16 kilometers. And now I would claim that 10 to 13 kilometers is much more likely, given what we know about neutron stars, in particular the 2 solar mass measurement and neutron star radius observations. So we've made a little bit of progress, and obviously we hope to continue to make more progress. So if you really do want to connect the dots, then we should look at some data points. Okay, we'll look at the non-LIGO data points first, and so this is the data. Okay, and so it's not really dots. Okay, you can't really connect these dots. The data is not that great in part. It turns out that for all the neutron stars for which we have some radius information, we have very little information on the mass. Okay? And so connecting these dots is quite a complicated endeavor. But the basic idea is relatively simple. You have X-ray photons. They enter your detector at some flux. If you know how the flux changes with energy, you have some idea of the effective temperature. If then in addition, you can measure the distance, for example, because the neutron star is in the globular cluster, then you can backtrack out R infinity, which is just the GR corrected radius. Okay? And so all of these neutron stars, they happen to be all in their each individual globular clusters. And because of these radius measurements, there's already strong evidence for the radius of a neutron star, of a 1.4 solar mass neutron star, to be less than about 12 kilometers. Okay? And so this is already stronger, for example, than the LIGO result, which I'll talk about a little bit later. At the same time, I have to confess, there are a lot of systematic uncertainties in these observations. In this paper recently with Craig Heinke and Slavko Bogdanov and several others, we've made a significant effort at tackling a bunch of these systematic uncertainties, but we really haven't, we don't have the last word on all of this yet. So even though we have the strong radius constraint, there are some systematics here, and these systematics are, for example, stronger than those that the LIGO collaboration has to deal with. Nevertheless, in 2015, absence of LIGO observations, I decided to charge ahead. I can use this X-ray data similar to what you see here, plus some other points which I'll not describe today. You can compute, in particular numerically, the moment of inertia of a neutron star. And there's a famous correlation between the moment of inertia and the tidal deformability. So the tidal deformability, you know just the tidal response, the response to the neutron star structure, so some tidal force. And so this output, this is the posterior distributions for that particular analysis. Now, you see there are 4 different posterior distributions here in these panels. And so I've varied the equation of state parameterization, or you can think about varying the prior distribution that I used to construct the equation of state parameters. In any case, you see that the moment of inertia of a 1.4 solar mass neutron star is likely to be between about 55 and 80. And this, because of this Yagi-Yunis correlation, gives a prediction for the tidal deformability. And transforming to a dimensionless version, LIGO used a slightly different definition. This result implies an upper limit of about 1,000 for lambda. And I will compare that with the LIGO result in a second. But before I do that and talk about that prediction vis-a-vis LIGO, I wanted to talk a little bit about these universal relations. Okay. One of the things my group is doing is trying to, playing devil's advocate, trying to break these relations a little bit. The most extreme example might be a strong first-order phase transition. And it turns out a strong first-order phase transition can have a relatively exotic impact on the tidal deformability as observed by LIGO. And so the example I wanted to mention here is a mass versus radius curve for a theoretical model that happens to have a strong phase transition at, let's look at the purple curve here. This strong phase transition happens at 4 times the nuclear saturation density. Okay, so even though the strong phase transition, this is a region in the equation of state where the pressure is flat. Okay, so it's a very strong effect in the equation of state. It's a relatively subtle effect in the mass radius curve. Okay, there's no, it doesn't have any kinks to it. It just sort of shifts to higher masses because of this phase transition. Okay. On the other hand, the effect on the tidal deformability is more significant. Okay, that because of the phase transition, you actually get a discontinuous jump in the tidal deformability at the one particular mass where that phase transition appears in the center of the associated neutron star. A slightly more exotic situation is here in the green curve, where this mass radius curve actually has a situation where you have 2 radii at 1 mass. So you have 2 different branches in the mass radius curve, and this means also you have 2 tidal deformabilities at that mass. And so in the presence of this phase transition, the tidal deformability as a function of mass comes down here, and it's multiple valued in this small region here. It has a small value and a large value, and then as you increase in mass, the tidal deformability drops according to this mass radius curve. Okay? And so these are the kinds of equations of state which really challenge so-called universal relations between things like the moment of inertia and the tidal deformability. In any case, to go on, LIGO did observe a neutron star merger. And so my glass half full interpretation is that LIGO confirmed my prediction. In particular, the LIGO paper says that their observation begins to compete with a 95% upper bound from X-ray observations. Okay. So that's the glass half full way of looking at that. Now, an even more glass half full way interpretation of this is that eventually LIGO will observe maybe, either LIGO or future gravitational wave detectors 50 or 100 neutron star mergers. And so at that point, they will, because of their systematics are different, they will be better at determining the equation of state than the X-ray data. Effectively, over the long term, I'm youngish, so I have to worry about this stuff. Over the long term, LIGO and other gravitational wave observatories will win. Okay? So that means I have to figure out, how to get paid. Okay, I have to convince the grant agencies that I'm going to do something else. So, but there's no no shortage of interesting questions that about dense matter that you can ask and that are relevant for other neutron star observations and astrophysical phenomena. In particular, mass and radius observations, observations of the tidal deformability, of the moment of inertia, these are all connected to the equation of state. The equation of state is a great fundamental thermodynamical quantity, okay? But it's not necessarily at all correlated with the composition because the pressure is an integral over the momentum distribution over the entire, from k equals 0 all the way to the Fermi surface and then maybe beyond. Okay? But the pressure doesn't tell you, because it's an integral, it doesn't tell you what are the degrees of freedom that are providing support for that integral. It's very easy to construct an equation of state in the neutron star core, which consists of deconfined quarks, which looks almost identical to an equation of state that's neutrons and protons alone. Okay? So this is one of the next tasks, one of the things that we will be able to determine. Also, superfluidity and superconductivity. These are modifications of the momentum distribution around the Fermi surface, so the pressure is not sensitive to these, but these have really strong implications for other neutron star observations. So basically, the way to proceed is to expand the data set. And in particular today, I'm going to talk about how temperature observations will give us more information about dense matter. So after 10 to 100 years, after it's born, an isolated neutron star, if it's not participating in some complicated accretion process, is isothermal up to almost the very surface. And that means the entire star is at one temperature, which means the equation that describes the thermal evolution is relatively simple. It's just the specific heat times dT dt and equals the luminosity. Okay, so all that happens is it cools. Energy escapes, either photons leave or neutrinos leave, and the temperature thus goes down. Okay. The photon luminosity is proportional to 2 plus 4 alpha. Alpha is some number that depends a little bit on exactly what's happening at the neutron star surface, okay? Because the photon mean free path is very small, okay? So the luminosity depends only on what's happening at the photosphere at the very surface. The neutrino luminosity depends on the composition and the nature of superfluidity and superconductivity. So this neutrino luminosity, this is where we get access to the properties of dense matter, which we wouldn't otherwise have access to. The way this equation works, basically, the lower numbers here win. So lower temperature dependence. So if you have a t to the 6th neutrino luminosity, that will cool the star very dramatically, where a t to the 8 temperature dependence is a very slow cooling. Okay. Very simple model is here. You begin at some temperature, and eventually your photons begin to cool the neutron star. Okay, and so this is the photon-dominated, you start with neutrinos. Okay, because the higher temperature sensitivity, this is the neutrino-dominated regime, and then this is the photon-dominated regime. So actually, the slope is 1 over one of the exponents. So this is like a slope of 1/8, and this is like a slope of 1 over 2 plus 4 alpha. So you cool by emitting neutrinos from the core until eventually you get to some colder temperature while this is suppressed, and then you just cool by photons from the surface. Okay? So very similar to the mass radius problem. If we have observations, basically dots, blobs, okay? and we can connect those dots by some theoretical cooling curve, then we can learn about the neutron star interior from observations. And so this is what the observations look like. So we estimate the age from p over p dot. We have observations of the luminosity or the temperature, and then we just try to connect these dots. And again, connecting these dots is sort of a non-trivial task. Okay. So in order to do this, so how has this been done? For over 20 years, this has been done by sort of chi by eye. Okay, so a theorist will draw a curve and say, kind of looks good. Okay, and so I want it to be a little bit more quantitative than that. So to start, I'll just start with one data point. Okay, and so this is my favorite way of presenting this. I have one Gaussian data point. It's centered at 2, 2 in some units, which I'm not telling you. And it's got a sigma of 1 in both direction, and there's no correlation. So that's my Gaussian data point here, this yellow blob. And I have two models, the blue model and the yellow model. Okay, so question is, which better fits the data? Okay, so I know most of you are theorists, but I still think data analysis is interesting and important. So we'll do a little data analysis for a second. And I'm going to go through a couple of the ways that people have tried to answer this question. Okay, it's sort of a fundamental question. Oops. Okay, so you could say, well, look, both of these curves go through the maximum of the Gaussian. And for that reason, they both describe the data equally well. And there's no problem with that, except for the fact that it prevents you from asking questions like, what is the expectation value of the vertical coordinate? Because these two models say something very different about what the y value is. Okay? The straight line model says the y value is sort of, it could be anywhere. It could be greater than 2 or less than 2, but the yellow model says it must be less than 2. And so these are distinctly different sort of interpretations, and we'd like to be able to distinguish the two. Okay? And so this leads to the following question. What kind of information, what do you have to do to this problem to really unambiguously decide what do you have to do in order to have a recipe to say the parabola works better or the line works better? Okay? And because obviously it's not obvious from the figure, and in truth there's no definitive answer without more information. Okay? It's a poorly specified problem. Okay? And so my claim is that basically in order to do this, did I already? Yeah. Okay. In order to do this, what you need is a metric. Sorry, I'm going to go back. So why do you need a metric? And of course, metrics you guys are familiar with, right? Because you do GR and differential geometry, maybe. And the reason is because you're taking two different kinds of spaces. One is this model space, which is somehow one-dimensional. Okay? Your model predicts a one-dimensional curve, and your data is somehow two-dimensional. Could be many reasons for this. This is a sort of generic situation, but you could imagine that the data has some sort of systematic, right? And that systematic is not something that we've modeled. It's just, or not something that we know how to model. It's just there, and we have to figure out, how to handle it. Okay? And so the analysis of neutron star data is a special case of this problem. We're trying to connect the dots, but you can imagine a general procedure in the context of Bayesian inference where you do a fitting of this type. And so you must specify, so there's a product over data points, this product over I, but we only have one data point, so just stick to I equals 1, and you can ignore the I index everywhere. And then you have the metric, okay? And the metric tells you how to do the line integral, because you just integrate the model along the data, and then lambda is your parameter, the way you parameterize the curve. Okay, so this particular form here is exactly the volume element, which ensures that your integral is invariant under reparameterizations of the curve. Okay, you don't want a different probability just because you've changed the way you parameterize the curve. Because we do Bayesian inference, then this parameter is also a nuisance parameter. You can imagine it has some prior probability. Okay, this prior probability is actually degenerate with the metric, but for some physical problems, it may be easier to specify one or the other, so I just put them both explicitly in. And then here, this d, this function here, is just the data point. It's just a function of x and y, which I've written x1 and x2 here because I'm doing this Einstein summation convention. And of course, on the left-hand side, this is just the c here is the integral along the curve. It's just what that means. Okay? So I'm doing a line integral, not a otherwise standard one-dimensional integral. Okay, so I claim that this is a very generic procedure, and for which you can answer this question. And indeed, depending on the metric, you find that either the parabola or the line may work better or worse. Okay. So what that tells you is that when you begin the Bayesian inference, you must find a way to specify the metric. Either the model will tell you what the metric is, or the metric is some prior choice. In other language, the metric is a prior choice that you've made. Oops, sorry. The nice thing about this, since we can do differential geometry, is it's very easy to generalize this to other kinds of problems. And in particular, if you have an m-dimensional manifold provided by the model, and it's embedded in an n-dimensional data space, then the form is exactly the same. All you get is this funny determinant, okay? Which you have to do over the indices mu nu, which now run over. It used to be a one-dimensional model, right? But now it's an m-dimensional model, so this determinant is non-trivial. Okay, so I talk with people from the Bayesian side and other physicists, okay, about this, and they universally hate it. Statisticians do not want to do anything with differential geometry. And in general, people look at this expression. I've gotten a lot of responses that's like, oh, do I really have to do that? Can't I do something simpler? And one of the advantages of this, it retains the sort of idea of coherence, okay, which is the great property of Bayesian inference that we all like. It says that you can't cheat, okay? So this is popularized by De Finetti. But it also is sort of self-discipline. It requires you to tell the reader or your collaboration exactly what prior choices you're making. And so I claim that basically a lot of works have applied simpler versions of this, but then not observed that they're actually choosing a prior distribution. In particular, they've already chosen the metric, and they haven't told you. So now I want to apply that particular method to the problem of neutron star cooling, because again, what do I want access to? I want access to something beyond the equation of state. I want to know the composition inside the neutron star, or I want to know something about superfluidity. Okay. And so today, I'm not going to get to composition. I'm just going to talk about superfluidity for now. So you can think of it 3 different kinds of superfluidity: superconductivity and neutron star interiors. In the crust, at low density, you have neutron singlet superfluidity. This is, again, so we have these nuclei. They're embedded in this sea of quasi-free superfluid neutrons. Okay. This isn't particularly important for us because the gaps are so large that neutron stars drop below this critical temperature very quickly. And thus, when you observe a neutron star, it's almost always the entire crust is paired. And so there's no variation in the theory. They're just all the neutrons are paired up. On the other hand, in the core, things are a little bit more complicated. You have proton singlet superconductivity, okay? And there are several different theoretical methods. I can say with confidence, because I come from the nuclear physics world, that the theorists have a real hard time agreeing on the gap, the proton gap. At higher densities, neutron triplet superfluidity becomes important. okay? And so these gaps, there are some, random curves here, okay? And these aren't even theory calculations. There's also a lot of uncertainty here in how the critical temperature depends on density, or as a proxy for density, you can think about the Fermi momentum of the neutrons or protons involved. So I want to determine something about the gap, but there's a lot of degrees of freedom here, and so I simplify the situation. I don't have to worry about this because the neutrons in the crust are always paired, but I have to worry about these two different kinds of superfluidity, and I say, well, these curves kind of look like Gaussians. So let's just use a 3-parameter Gaussian model with some maximum critical temperature. There's some density at which the critical temperature is maximized. And then the Gaussian has some location just in density or Fermi momentum. And then the Gaussian has some width. And so because there are there's proton superconductivity and neutron triplet superfluidity, I have 6 parameters. So going back to the basic picture here, I want to connect the dots. Okay, but of course I mentioned that I have to choose a metric, and so what I actually choose is a trivial metric in log time, log temperature, which is not obvious choice to make. Okay, but this is effectively what everybody has been doing for decades, and so I do the same thing. The motivation is that the observational data tends to be somewhat Gaussian in these two variables. The observations are log normal. It's not unreasonable. Obviously, times and temperatures are both positive quantities. Okay, so this is the choice that's often been made, and I retain that choice for this particular work. Okay, and I wanted to talk about how the superfluidity plays a role. First of all, it turns out in the case of a superfluid fermion system, when the critical temperature is, when the ambient temperature of the medium is near the critical temperatures for superfluidity, what happens is thermal fluctuations can break Cooper pairs, okay? But you know that if you break a Cooper pair with a thermal bath, you can also reform that Cooper pair. And when you form that Cooper pair, you gain the pairing energy. And so typically, you can imagine taking that pairing energy and sending it back to the thermal bath and being at some sort of equilibrium. But you can also use that energy that you gained in forming the Cooper pair to create a anti-neutrino pair. And so this is this funny modification of the Bremsstrahlung rate, this Cooper pair emissivity. So that is that you form a Cooper pair and use that energy to create a new bar, and then that takes energy away from the star instead of heating back up the thermal bath. Okay, and so this is the sort of T to the 7th-ish process, okay, that is most sensitive to the superfluid gaps. And in particular, this process really drives the extent to which curves match or don't match the data. The other important cooling process, which goes like temperature to the 8th power, is the so-called modified Orca process. And it's just beta decay, but beta decay doesn't quite work in many situations because of energy and momentum conservation. It needs a spectator nucleon, so we have an additional neutron on both sides of the beta decay process. Okay. There's also some isospin variants of this that I haven't written down explicitly. Okay, so this is how our neutron star cools. It's obviously connected to superfluidity, and so if we analyze the data, hopefully we get access to the superfluid gaps. We presume, similar to BCS theory, that there's a simple relationship between the critical temperature and the maximum value of the gap, between TC and delta. And so I sort of have a bad habit of switching back and forth between these at will. But basically, it's easiest to talk about constraints on the critical temperature. So we did this analysis in a recent paper, and what we found, these are two different analyses on the top and bottom. What we found is that the results on the superfluid gap are very sensitive to just a few points in the data set. not the kind of situation we would like to be in, but nevertheless, it's good to know about it. And so you see that the cooling curves are sort of qualitatively different. They're sort of thin and thick here. The uncertainties change quite a bit. And the big difference between the top panel and the bottom panel is the Vela pulsar right here, B0833. Okay? It has a relatively accurate temperature measurement and a young age. Okay? And so in order to so what happens is if Vela is there, in order to reproduce the young age, it forces the neutron triplet gap to be small, okay? Because then so what is, sorry, did I do this? If the neutron, that means that there, so there's an impact on, I should have explained this. Okay. The more superfluidity you have, the more Cooper pair emissivity you have. And so it makes for a colder cooling curve. However, the more superfluidity also tends to suppress this modified Orca process. Okay? So if these two neutrons are paired, it's unlikely that that one of them will want to beta decay because you have to break that Cooper pair. Okay? So there's a sort of push and pull. And that's what I got my words twisted around. But basically what happens is that with Vela, you end up with a smaller neutron critical temperature, whereas if you take it out, the critical temperature for the neutron superfluidity becomes larger than 10 to the 9 Kelvin. Okay? So it's not necessarily a very comforting result, but for me, what was significant about this paper is we're actually starting to be able to quantitatively ask and answer these questions instead of just doing simple chi by eye. Okay, so for the last part of the talk, I wanted to talk a little bit about this new collaboration, this Teams collaboration. This is a DOE's, the Department of Energy in the US, the CITA collaboration. So we have a dozen different institutions, including national labs, and a bunch of computer time on large systems. And the idea is to improve our simulations of core collapse supernovae and neutron star mergers. Obvious motivations, because this is, you know, from the nuclear physics side, are to address the long-standing question of how stars explode and why they explode, and then, of course, to look at our process nucleosynthesis and neutron star mergers, but also, to, of course, because motivated in part by LIGO, because LIGO is measuring neutron star mergers, and eventually gravitational wave detectors may detect the gravitational waves from the post-merger remnant, and so making these simulations more accurate is a high priority. So my claim is that simulations like this, and in particular future gravitational wave data, will require substantial theory input from simulations of this kind before we truly understand what's going on. And so what is the theory input? Well, we need the equation of state, which I talked about before, but also we need to know how neutrinos pass through this kind of matter. I'm going to ignore the neutrino part and just talk about the equation of state, because this is what we've worked on so far. So we need to know the bulk thermodynamics, the equation of state, over a very large density, temperature, and isospin regime. So we need the highest temperatures in a merger may be up to 150 MeV. This is significant because this is near the pion mass. Large density range is important. And then, of course, neutron stars are very neutron rich. And much larger than Z, but also at lower densities, the number of neutrons and protons is nearly equal. And so this big, of course, neutrino trapping may also be important. But these three here form a large three-dimensional space over which I have to construct an equation of state. And in particular, in this three-dimensional volume, different regions of that volume are connected to different kinds of nuclear physics. So at low densities, especially in matter with only neutrons, okay, at very low densities when the neutrons are very far apart, they only occasionally scatter by each other. And only the two-body scattering is important because it's very unlikely that 3 neutrons will ever be close enough for the 3-neutron force to matter. Okay? So because we can do scattering, we can measure the scattering phase shifts. And the quantum mechanics says that the phase shifts contain all the information, and in particular, you can directly compute the equation of state from those scattering phase shifts. And this is done in the so-called virial expansion, which has been known for many years. And so we would like, in the proper regime, okay, in dilute neutron matter, for example, we want to make sure that our equation of state reproduces the virial expansion, since these phase shifts are determined from experiment. There's also a lot of nuclear physics data, and we want to respect that data. In particular, there's a whole Segre plot of all the isotopes. We know something about the nuclear masses and charge radii. And so we would like to have a model which respects those experiments. There's been progress on the nuclear theory side for pure neutron matter near the saturation density. This is now not dilute matter, but dense neutron matter. Okay? There's been significant progress in the theory side. Also, in the finite temperature part, matter beyond the saturation density, well, the cool thing is that we have neutron star radius observations, so we do know something about what's going on in the equation of state at high densities. We don't know everything, okay, but we're making progress there. And then this last thing is what we really need. We need to know, because in the outer regions of the neutron star are not just neutrons and protons, there are nuclei there. We need to know how those nuclei are changed because of the fact that there are these superfluid neutrons around, or because of the finite temperature. So the way we're going to tackle this, I'm going to use Bayesian inference again. And the cool thing about Bayesian inference is you can be somewhat iterative about it. If we have a couple different data sets, I can just take my prior distribution and multiply it by, do successive inference, okay? Especially if these two data sets are uncorrelated. As you would expect nuclear experiments on, nuclear structure experiments to be relatively uncorrelated with neutron star observations. Also, if your model is just some direct product, then you can imagine separating the inference this way, and this latter term here just becomes a prior distribution for this second inference, something like a prior distribution. In any case, so sort of many of you are experts in Bayesian inference, but just to explain in pictorial form, we have a lot of nuclear experimental information, okay? And we have neutron star observations, neutron star radius observations, and maybe eventually information from more information from LIGO here. But we can view this inference problem and this inference problem completely separately. So this has been done. There's a different DOE collaboration which is really interested in nuclear physics and the nuclear experiment. They do their own Bayesian inference. I don't have to worry about what they do. All I need is their results. And then I have the analysis of the neutron star mass and radius data, which is completely separate. And then I just multiply those together with, now I have to put in the rest of my model to complete my equation of state in this three-dimensional space. I need to, one easy way of parameterizing what's happening at high density is through the speed of sound. So there's a speed of sound parameter. I have to put in some nuclear theory. And so there are 4 different parameters here which have their own prior distributions, which is part of the Bayesian inference that we're actually doing. And so effectively, we have these 1, 2, 3, 4, 5 parameters. And then we just have these previous inference calculations. These are actually, this is a 12-dimensional space. This is a 10-ish dimensional space. Okay, these are larger inference calculations, but I don't need to worry about the size of those parameter spaces because all I have to do is there's some Markov chain. So those previous inferences have constructed this Markov chain, and all I have to do is select rows from the Markov chain. Okay, this is something.
Is it the choice of skirm EOS that constraining?
That's an excellent question. In this particular calculation, we assume that matter consists only of neutrons and protons. So that makes it a little bit better. But then again, this speed of sound is another correction we have to make because the skirms become acausal. Their speed of sound becomes larger than the speed of light, and so we have to fix them. We don't use the skirm for neutron matter because there's lots of nuclear theory input there. So it's not. Well, it's for nuclei, but also we have to use the skirm interaction for isospin symmetric matter above the saturation density because there's absolutely no observations or experiment there.
EOS had issues near certain.
Yeah.
Curvature near saturation density.
Yeah. So let me finish this next slide, and some of those issues will become here. So just to explain some of the nuclear physics sides, this nuclei collaboration is the collaboration that I'm not a part of that does the inference for the nuclear structure. Okay, and they have some 12 parameters, and this is their output. Okay, you see these aren't necessarily totally Gaussian. But they have a posterior distribution. Now, we weren't able to use all of their models for exactly the kinds of issues. In particular, what happened is their effective masses become infinite. Nucleon masses cannot be infinite, even in medium. And so there are a couple problems with the way the skirm interaction treats the difference between neutrons and protons, the isospin symmetry. So we had to fix those. In any case, except for this last issue of nuclear structure, we believe we've addressed all of these issues. We use the virial expansion. We use skirm matters selected with the Markov chain. We use nuclear theory results in both regimes here. We use neutron star observations, again, a separate Markov chain. And on the output, we get posterior distributions for the equation of state. And one way of saying this is we can do uncertainty quantification. So at 3 times the saturation density in neutron matter at low temperature, I can tell you what the free energy per particle is, and I can tell you what the uncertainty is. It looks kind of Gaussian. Okay? And so instead of one equation of state table, I can generate thousands of equations of state tables selected according to their proper probability. Okay, so just to talk about the state of the world here, there are right now about a dozen sort of popularly used full equations of state for neutron star merger and core collapse supernova simulations. They hate the idea of using 1,000 equations of state because they can never get enough computer time for that. Okay, so that's okay. Part of this is just that I'm going to compute the correct equation of state, and in terms of their computational science problem, they have to solve that, right? But also the important thing about uncertainty quantification is we can select extreme models carefully, and we can be quantitative in terms of how extreme they are. And finally, it turns out that some of the equations of state that are currently used are really actually quite improbable from what we know of current nuclear physics and neutron star observations. So just to summarize, of course, we're continuing to constrain the equation of state, X-ray observations, LIGO. I talked a little bit about these methodological developments in terms of how we do this fitting. And then we're going beyond the equation of state. We've got some work on the superfluid gaps, and the next thing we're tackling is the composition. And finally, at the end, I talked about these new equations of state, which will be important in interpreting these big simulations that are currently done. So thank you very much for your time.
to the previous slide. I'm just curious, so for these two different plots, the difference, I'm sure the NB parameters, not just the...
So the NB is the number of baryons per unit volume. Okay. My apologies, I should have defined that.
I figured that was. Is it problematic that, like, for some of the equation of state we use, like the green one is off for both, but then other ones like the red one is really off for one? Like, is it problematic for some of these other equations?
Yeah, so yes, I do believe it is. So with the green curve is actually this Latimer-Swesti and is very commonly used. The Latimer-Swesti code itself has a wide variety of options in it, but it's most frequently used with a particular kind of nucleon effective mass. And so what's done most often is that code is they choose a relatively large nucleonic effective mass, which tends to be ruled out when you do the Fermi integrals this particular way. And so I do believe that's an issue for this equation of state. The red one, also the same reason. And I think eventually we'll start to stop using these equations of state for that reason. The other problem, yeah, so it is problematic. There are some detailed nuclear physics issues, and we'll see how it goes.
Can we go back to the differential geometry integral you looked at? I guess the evidence?
Yeah, the multivariate one or the simple one?
Whichever one, multivariate's fine. I just wanted to understand what's going on here. So this is in some sense your assumption on the likelihood?
This is, yeah.
And what's in some sense the underlying picture here? Your data are themselves probability distributions in this larger space. And you're essentially looking at the volume-weighted overlap of those probability distributions with some model shape.
Right. You're just, so basically you're just doing, oh, that's interesting. You're just doing line integrals, right? So this is the data that forms the two-dimensional background, right? And you're doing a line integral, and your lambda is your parameter that takes you along the line.
You have the freedom to choose a completely separate metric along that line.
Right, because, and part of the problem is, one way to think about it is that lambda need not have the same units as x and y. And so you have to sort of resolve that unit difference.
Questions? So like for what you've done, you said you chose the metric time and temperature?
Oh, yeah. So I choose it. So a trivial metric in log time, log temperature. So this is in the data space, right? So if you go to, this is a very non-trivial metric in temperature and time without the logs. But that's okay. It just means that if you make some sort of variable transformation, you have to carry everything with you.
What equations of state are your colleagues doing core class using that?
Oh, right now, so LS220, SFHO, really popular. The IUFSU is pretty popular. There's another one called DD2. Which is not plotted here, which is relatively common.
But still using LS220.
Oh yeah, and there's a couple others.
Isn't that a problem with the maximum mass?
LS220 doesn't. IUFSU originally had a problem with the maximum mass, but that was sort of fixed. Then also there's a couple Japanese, the Shen and Toki. The old Shen et al. Equations of state are also occasionally used. There's some new ones with hyperons. And,
Well, if I actually have a question, to what extent does it matter? To what extent do the uncertainties in the simulations cover any issue with the equations
Yeah.
of state?
that's an excellent question. The problem is until we do this, we don't know. So what's done now is in some works vary the equation of state, and they do, they choose 2 to 4 to 5 equations of state, and they just reproduce their calculation. Unfortunately, what happens is they're changing many variables at once, right? So there's no way to sort of decompose what the real physics is behind the changes, in terms of nuclear physics, behind the changes that they see.